Okay, so we're starting from a model that's linear elastic, solid mechanics. We have an elliptical hole. We've looked at stress concentrations near this elliptical hole. So if you were to zoom in, we see behavior like this. We haven't done any kind of verification or convergence analysis, but the point is to set this up and then move toward plasticity. So let's see if we can get that in the model. And I'm going to try to remember where we start. So let's see if we can add physics from under the model. Let's see what this gives me. So hopefully this is going to be the correct method. So sticking with the notation from the notes, I'm going to call this GAM, short for gamma, the shear plasticity coefficient. And where's my... oh. And going forward, this is also time dependent. Okay. So yes, this is what I wanted. So I'm gonna, so you just don't get confused, I'm gonna relabel this. I'm gonna call this elas. Let's call it plane elasticity. And the second PDE, I'm gonna call this dislocations. Alright. So I'm not going to work this out by hand. I'm going to give you the variables C1. I'll define these later. C2. And the important part is this term. And I'm going off memory. I believe this is negative. We'll check it later. So in the assignment you have eta minus tau. However, there is also a time-dependent term. I believe that is positive. And then this is gam t, so time derivative on gamma. Alright. So in this problem, remember, everything defaults to zero flux, and with this problem, we're going to say that there's zero flux on the boundary. So dislocations can basically move throughout. All right. The places where that may not be true is if this was say a hard boundary. So if this was constrained with some kind of grain or some type of structure that dislocations could not flow into, then you may need to change that. But this is an open boundary, so dislocations can move through this open boundary. Alright, so we need to define some things. We need eta. So from the assignment, we have a constituent parameter A times gam. We have Z1. I'm going to define a naught gam x, so this is a gradient in the x. C2 a naught times gam y. So these two terms will give diffuse interfaces, so we're just using that to smooth out any potential discontinuities. I believe that that's all we need. Let's go up here. Let's add beta. For now, I'm going to put this at 0.1. We'll check that later. I need an A naught. Actually, let's first define A. I'm going to put A on roughly on the order of the elastic constant. Let me change this. So that's the resistivity for motion of dislocations. And A naught will be put it 1,000 times smaller than that one. We keep that to be fairly small so it doesn't heavily influence the solution. Okay. So those are material parameters. We have this. There's still a few other things in here we need. We need tau. We're going to make a few modifications to this as we develop the model. First, let's put in the slip direction and slip plane. That's times sigma x. The shear S1 times M2 plus S2 times M1 times the shear plus S2 M2 times SYY. Alright, I'm leaving out the indicator function for now. We'll come back to that later. We need to put in an angle. Let's say TH will be 0, and okay, if you want to put this in degrees, put it in this way. So that means this will be 0 degrees, or let's just say it's 30 degrees. Okay. So make sure that's in radians. Now S1 will be cosine theta, S2 sine theta, and if memory serves correct, this one will be sine theta M2 minus cosine theta. Alright, I think we've defined everything. Let's go back and let's check our PD. Alright, looks reasonable. Let's see if this will solve. Now I have two studies here, so you have to be careful on what's transpired under here. Okay, so that was for, I guess, elasticity. So let's go to this one. And we're going to try to solve these together. We're just going to let this go to 0 to 1 for now. And just so we have an idea on what's happening, instead of plotting the stress, let's put in GAM. Alright, save it one more time. And error. Ah, okay. I have a typo. Okay. Duplicate. Alright, let me work out a few bugs and then we'll get this running on the next video.